Welcome to a second video on the integration of structure, daylighting apertures, and HVAC in the roofs of buildings. So we had a previous video for Chapter 1, Section 9, Subsection 5 on coordinating structure, daylighting apertures, and ductworks in roofs. We're now going to do a second video, which we're going to add the letter B. So in the past, when we've had multiple videos associated with a subsection, we've labeled those with the letters A, B, C, D, etc. Our previous video was presented as 1.9.5, and there was no A there. So in this case, I've just put in a grade in A, and eventually we'll go back and change that nomenclature in Moodle, but I don't want to change it now. I don't want to switch horses in midstream. You have a schedule with appropriately labeled video names, and I don't want to confuse anybody by suddenly changing the lettering system. But we are going to add a B to this to indicate that it is a follow-on to this previous video. In that previous video, we presented this idea of this daylighting system involving vertical, north-facing, and south-facing glass. So in this case, this entry would be on the south side, or it could be called the north side, because for the purposes of this drawing, we haven't made any differentiation between the north and south apertures. But let's say this is the spine of the building, and this was a design actually for a library to be built in a small city in North Carolina. It eventually was built differently because the budget was extremely limited and they wanted more money for books, which is perfectly understandable. But this was to be a fairly substantial and beautifully daylit library. The spine is running from the south to the north. The spine is accentuated by raising the roof and introducing these triangulated apertures facing both south and north. Most of the circulation was to occur along the spine, and there were other special functions that occurred there. And then the primary reading rooms were off to the east and to the west. And you'll notice I've put in some of the roof panels. There's a lower roof panel and an upper roof panel, and the light is entering through this south-facing aperture. There's another aperture on the other side of this raised portion of the roof. That aperture is facing north, and the combination of north and south makes a very good lighting system. It has some of the brightness and energy of south-facing glass, but which admits beam sunlight. Of course, in this situation, there would need to be something to intercept the beam sunlight so it doesn't come down to floor level and actually hit people in the eye. But that light would get diffused around, and on a bright, sunny winter day, it would make the space a lot more cheerful. But the north light is there to avoid the extreme fluctuations with the coming and going of clouds. So the north-facing glass is very uniform and tends to smooth out somewhat the light that's being introduced from the south apertures. Now, we subsequently made some adjustments to this concept. You'll notice in this case, there were beams running between these trusses, and that might in fact be the way all this would be done in the end anyway. But there is a simpler version of this, which says that the corrugated decking can run from beam to beam, or excuse me, from truss to truss if that corrugation is deep enough. So some of the drawings I'm going to present, which are related to assignment 5, will show corrugated decking, and as long as it will span the space between the trusses, that's a structurally legitimate way to do things. Now, some of this substructure here, like these beams, and then some cross bracing associated with those beams, would probably be crucial to keep the building aligned and stable until the corrugated decking can get screwed down. So you're not going to be able to get rid of all those purlins and all that substructure, but you will significantly simplify it if you run the corrugated decking between the trusses. Okay, so one of the things that we did was we talked about this scheme where instead of those corrugations, instead of these trusses just going down the depth of the aperture, to get greater structural depth and to simplify the construction, we came up with this idea that we'd have a truss that goes from a finished ceiling across the bottom up to the bottom of the upper roof decking. The upper roof decking would be basically horizontal in the long direction here. That means the top chord of the truss is horizontal and the bottom chord of the truss is horizontal. Now, you'll notice in this drawing, this was an early rendering of what this might look like. There's no ductwork. So as we discussed the need for ductwork, we said, let's run some trunk lines in this spine, and then those trunk lines could inject air uh, through this space and out to the boundary of the space. And that was part of the idea of this concept, which is the spine of this building is over here. There would be some kind of ductwork or trunk line here, which would then dump air into this volume, which is above this finished ceiling, but below the tapered decking of the tapered portion of the roof. You'll notice you need the most airflow here, but as air is delivered to the space, you need less and less. So this tapered volume works beautifully in terms of delivering air because the duct is basically getting smaller and smaller as less and less flow is required. On the other hand, on the top surface, we have a tapered roof surface that assures positive runoff of the water from the roof. The amount of flow is lower at this end, but as it flows downward, it accumulates more and more falling rain. And so there's also a tapered volume for the water runoff. And fortunately, the tapered volume for the water runoff needs to be deep at the outer or perimeter end of these trusses, and the tapered volume for the air transport needs to be the highest at the other end at the interior of the building. So it's a very, very simple concept. You can't see it too well in this section, but the idea is that there's a finished surface, and in this case, this top edge is the top edge of this light well, which allows the light from the two glazing elements to enter down into the space. So this particular version, which is shown in the previous video, the length of this bay from the interior columns that occur between this wing and the spine of the building, which is over here. The distance from this column line to the column line at the perimeter of the building is 60 feet. I'm calling that the length of the bay, and we're measuring the length of the bay parallel to the daylighting aperture glass. And then in the perpendicular direction, which we sometimes call the profile section, where we see this change in shape of the roof. The dimension is 30 feet for the bay, and we're saying there are two monitors in that bay. Now, you could say the bay is actually 15 feet wide and it has one monitor in it. The numbers are slightly different, but the output of the numbers or the calculations for sizing various parts of this don't change, whichever of those two ways you choose to characterize it. I drew this bay with two of these showing just because I want to show the repetitive nature of it. But you could just draw one of these bays and say that's going to be replicated over the full north to south dimension of the building. Okay, so here's the deal. You've been asked to construct a system somewhat like this for assignment 5, and the purpose of that exercise is for you to start understanding that when you construct a scale drawing, you begin to discover things and understand the system. And the first few times you would draw something like this, you draw it and then you'll think, oh, I forgot this or I forgot that. Just like when I drew this, I kind of left out the ductwork, but then I went back and said, okay, let's rethink it with ductwork. And that's how we came up with this. So you're going to start practicing sizing the glazing, sizing the curb height to accommodate the water, accounting for the slope of the lower roof in order to make sure you have positive runoff of the water. The longer the bay, the greater the vertical change between the high end of the sloped glaze of the slope portion of the roof and the low end of the slope portion of the roof. And that's going to impact your truss height because the truss height has to accommodate the height of the glass, but it also has to accommodate the curb and the sloped roof and some amount of air delivery at the end of the air. So in this case, I don't remember why I ended up, but I had 6.5 inches right there, I think in the assignment I gave. And in the problem I'm going to work, we're going to make that a nice round number, which is 6 inches. And by the way, in this case, I've drawn a 1/2 inch thick piece of sheetrock. You have to be careful though. I'm not designing the roof in detail, but if you were going to do this building, you'd need to do that. And different kinds of ceilings have different depths. For example, if you wanted to support this sheetrock, you could run ceiling joist from one truss to the other. Those ceiling joists, though, would be oriented in a way that they're tending to block the airflow. So one of the things you could do is you could hang this ceiling with using wires and hang it from this corrugated steel decking up above, or you could not make that sheetrock. You could make that hung ceiling tiles, in which case you'd have 1.5 deep aluminum T's supporting the acoustic panels, and then those aluminum T's would be hung off of the corrugated decking. All that really needs to be worked out in the end. And by the way, your engineer won't do that for you. You're the architect, and you need to think about what those finishes are. But for right now, just to kind of get us started on this and not get totally bogged down in some of these details, we're just going to represent that ceiling with this 1/2 inch piece of sheetrock. And we all understand in the end that ceiling is going to be a little different. And whatever it is, it might tend to interfere with some of this airflow, in which case we may need to increase the height of the truss to accommodate whatever the depth of that ceiling structure turns out to be. You'll notice here that I said SFR equals 20%. The term SFR stands for skylight area to floor area ratio. And some people have picked that up and they're still applying the term skylight, even though this is a roof monitor and it's not a horizontal aperture, but it's a vertical aperture system. And so I ended up using SFR here of 20%, but in subsequent lectures, I'm calling it AFR, which stands for aperture area to floor area ratio. And for this system, we're going to make this 20%. If you're creating a space where people are going to be doing almost exclusively computer work, you might want to make that AFR 15%. If you have a space where people are going to be doing some particularly challenging and critical visual task, you might make that AFR 25%. This will be partly a judgment call on your part, but it also, we have references for what kind of light level you need for various kinds of tasks, and you can get that from the Illumination Engineering Society of North America, which prescribes light levels for various kinds of tasks that need to be performed. So, for example, somebody who's doing jewelry fabrication or watch fabrication or watch repair, or even certain kinds of artwork might need more light, in which case you might want to kick this AFR up to 25%. Okay, sorry. So the purpose of this particular lecture is to get you started thinking about how to determine the dimensions and sizing of things in this drawing, this system that you're drawing up, and also the process of how you draw it to scale. And I'm going to start with the AutoCAD file, and I'm going to spend a little time in that AutoCAD file doing some really basic things, which I think most of you, I hope, already know how to do. If not, this is going to be a fairly time-consuming assignment. Okay, so first of all, let's go look at what your assignment is. I just took this drawing and I said, I want you to resize it. So in the original drawing, I had 30 feet here. It said, make that 60 feet. I had 60 feet here. I said, make that 120. You're still going to have an aperture area to floor area ratio of 20%, and that's what's going to tell you how to size this glass. And I'm going to work an example here. It's not going to have exactly the same numbers that yours does. I'm going to make this 100. and I'm going to make this 50, and I'm going to be using slightly smaller members on my trusses. But this will get you started um, and show you how it can be done. And before I do that, though, I'm going to show an example of in more detail because you can't really read that drawing that I was just showing you. So here's that drawing with the sloped insulation. This insulation up here will be tapered so that water can drain off each side. So I've drawn a section here that shows that tapered insulation. So rainwater comes here, pours over the edge, and then this surface is sloped downward. So this is the section at the high end, and then everything else looks exactly the same except this lower level of roof here. Um, the lower roof has sloped downward, and now there's only 6 inches of air gap here to conduct the air that we're pumping into the building for thermal conditioning or for air quality purposes. Okay, so you can go look at this in this particular drawing. I have 3-inch corrugated decking that's spanning um, from, so that's what this is. And I'm going to move this so it's a little more readable. That's 3-inch corrugated decking that's spanning from the top of this truss to the top of that truss. And by the way, there's symbology or shading that you can put on all kinds of things, like steel is typically this two closely spaced lines with a little more of a gap, and then two more closely spaced lines. So right here, and I messed up this drawing somehow because something here is slightly sloped. Let me just see here. It's like I got this little piece right here slightly out of whack, but I don't want to spend time right now fixing that. So these trusses are double angle trusses. So you'll see that there are two angles here that represent the top chord, and likewise we have that down at the bottom chord also. This is an oddball truss though, because I know it's pretty deep and I don't want the web members to buckle too easily, so I'm not going to use a single angle there. I'm not even going to use double angles. I'm going to use a 2-inch by 2-inch square steel tube for the truss webs. I'm not only a little concerned about those things buckling, but you'll also notice that I'm attaching some angles that are going to get welded or connected in some way to these web members. And then I'm going to have this 3-inch decking resting on that. And the way these lines are stopping short is a little confusing to you. So I'm going to go over there and we're going to say that 3-inch corrugated decking is going to rest on that single angle. That single angle will be welded to this web, but the decking is creating an eccentric loading on that angle, which is tending to bend this web member or the web members to which this angle attaches. So that's why I'm going with a 2-inch by 2-inch square tube because it works better in bending and it's more resistive to buckling. In fact, now that I look at it, I'm thinking I probably should have made that a 3-inch by 3-inch square tube. I also wanted to clean this up a little bit for you, like drawing all these double angles is really tedious. And So I'm going to propose that on your trusses, the cords are going to be square steel tube also. I'm going to use, for my 100-foot long trusses, I'm going to use 4 inch by 4 inch steel tube. You're going to use in your initial drawings 5 inch by 5 inch square tube. Now, I know this seems like a lot of trouble, but you're going to draw this up, and this would be the first step in your evolution of this system. You'll draw it up, and the engineer will then look at all your dimensions and understand what it is you're trying to do. And your engineer will go back and do the structural analysis on these trusses. And your engineer will either say, for your particular design, where you're spanning 120 feet, that 5 by 5 tube makes sense, or your engineer might come back and say, we really ought to go with some larger dimension like 6 inch by 6 inch. Chances are the 5 by 5 will work. In some cases, like for the cord members, it might end up with a fairly thick wall, but to, to first order, your engineer can tell you what the wall thickness needs to be to handle all the various forces that are going to be propagating through your structural system. And your engineer will say, well, okay, certain parts of this need to be 1/4 inch, some parts 3/8 of an inch thick, some parts might even need to be a 1/2 an inch thick. If it's determined that it might need to be a 1/2 an inch thick, you might decide along with your engineer that you want to jump up to a 6 by 6 square tube. And I'm going to draw it up based on square tubes also. And we're going to make the web members the same size as the cord members. Now, the web members can typically, they have less axial force in them, and so they can typically be smaller than the cord members. But there's a problem with bringing, say, a 2 inch by 2 inch square tube up to a 4 by 4 square tube cord member. And that is that the force in the web members is tending to jam into the thin wall of the cord member, and that induces bending, local bending in the wall of the cord member. That local distortion creates stress on the welds, and so to give you really simple joints that you can rely on, we're going to make the web members the same width so that the interfaces of these cord members can be welded to the interface of these web members can be welded to the interface, and by inner, I mean towards the interior of the building. And you get a direct weld connection between the walls of the two tubes. And the same happens on the outside. And so you'll get a better truss system if you do that. And it will be beautiful and clean in a way that double angle trusses tend not to be. Mainly, though, I'm just doing it this way to make it easier for you to draw it because um, there's a fair amount of work that's going to be required to pull this off. Anyway, this seems like a lot of work and you're going to draw it up, but this is how you make sure you are communicating with your structural engineer and you're not doing sort of sloppy drawings or just verbalizing. I know an architect who um, manages to direct major crews of people mainly without drawings. He just waves her hand and communicates. And I've seen her do this with a crew of 6 people where there are 3 different languages she has to speak along the way. Typically, though, this is a disastrous way to try to do things. You want to draw it carefully enough that everybody on your team knows exactly what you're talking about. And you can sit and fine tune it together without somebody going off with a misconception about what you're trying to get done. And then they come back and they've spent a lot of work doing an analysis. It turns out they're not even analyzing the correct thing. Okay, so we're going to talk about how to draw this. And by the way, here's this half-inch sheetrock ceiling, which, as we said, may not be sheetrock at all. I've shown it folding up here to create a light well, but I also have it doing that because we're talking about this as a volume for conducting air, and that doesn't work so well if there are no sidewalls to it. So um, this will have to be framed out, and you as the designer might come up with something you like better than that. But I'm trying to let you know why it does this weird thing. So this is a kind of finished surface which defines the light well. And by the way, these walls right here that let the light go down through, we call that a light well. It's a vertical shaft. Um, and inevitably, there's something like that there. And in the last video on this topic, I talked about ways of sort of pulling back and creating a triangular structure underneath so that this light well is not so deep. Because the light well is really your enemy because some light comes here and it hits that, and you're going to make that surface as white as possible, but even a white paint surface absorbs light. And so this light well, you want to make it as shallow as possible, and you also want to make it as white as possible. And so finishing it out in this manner helps with all that. So this slope right here should be at least 1 in 50, or we say a quarter of an inch vertical for every foot horizontal. And I did this pretty approximately. I'm mainly trying to show you that just like this lower surface, which we're sloping in order to get positive runoff, we also want to get positive runoff from the top surface of this upper part of the roof. Now, here's something else I've done here. I drew a vertical line and then I tilted it out 12 inches. That's the profile angle, the minimum profile angle that we say a roof monitor system should have on the south side. I think in the notes I said that should be somewhere between 12 and 15 degrees, and I just picked 12 degrees. And I'm putting it there to remind you that we do like to have some overhang on the south side. And by the way, I'm going to go back and I guess I shut that up. But typically, this is more like 15 or 16 to 20 degrees if we only have south-facing apertures. But because the south apertures are only half of the glazing, we're not going to get severe thermal overloading, so we're not putting out quite as big an overhang on the south side. And when you go to detail this on the north side, probably you're going to have something more out there. So you might decide, for example, to extend this whole thing outward and provide some insulation and get the water further away from that glazing. But assuming the glazing is sealed properly, you don't need an overhang on the north side, and the less of an overhang you have, the better. Now, there are some problems with this design. First of all, the customary thing we do here to protect this insulation is we'll bring this bent out here, and it looks sort of like an angle, a steel angle. There's this vertical face, which in this case is 8 inches high for this drawing. For yours, it'll be a bit more than that. And I think it's like 1.5 feet in this direction on the horizontal. It could be an angle, but nobody rolls an angle with a thin wall that's that large and unequal legs. You just can't get that, but you can get sheets of 1/4 inch thick or 3/8 inch thick steel plate and have them bend it to provide this structural function. So this gets welded to the top. This angle up here gets welded to the top cord of the truss. And in your case, the top cord of your truss will be a tube, so it's pretty good from a torsional point of view. But it's also true that this decking is sticking out sufficiently. Not sure. Sometimes I put construction lines in there, and I can't remember why they're there. But this angle also comes up because on roof edges, people have this habit of laying a ladder against that edge. And so you can't have this so-called rigid insulation. It's more rigid than soft insulation, but it's not very rugged. And if people bash the edge of it with a ladder, it's going to damage it. So we have this angle here that comes up and seals off the end of our 3-inch corrugated decking. In this case, we have 5 inches of rigid insulation. Keep in mind, I'm putting numbers in here. Depending on the quality and thermal value of the insulation, this could be 5, could be 6, could be 7 inches. So I kind of play with this number in a random way just to let you know that that's not an absolute fixed number. So this 8-inch leg of this bent is protecting and sealing off the corrugation. It's protecting the rigid insulation. But there's a problem because outside air is hitting this bent and then conducting through this plate to the inside and also conducting into this 3-inch corrugated decking. Now, in this part of the world, we have these kinds of thermal bridges. As time goes on, we're going to have to do a lot better with these things. We've made some progress in the last 50 years since I've been in architecture, but we still haven't solved them all. The Canadians are much better at this than we are because they live in a much harsher thermal environment. But I don't want to labor too much over this. I want you to be aware, though, that there's a certain angle that we're trying to extend out, that we need this structure to get out there and support this fascia piece, which is there to protect the outer edge of the building. I want you to be aware of all that. And by the way, I've drawn in here some kind of aluminum extrusion. And then I have some kind of, this green thing is neoprene of some sort. But what I've shown here is not very realistic because this whole assembly will probably be split in half and there'll be some kind of screws that are used to squeeze the neoprene up against the glass. And I don't have the time right now, and you don't have the time either to work out all those details, but there's enough of it here to remind you that that still remains to be resolved. I've also put a 4-inch deep piece of aluminum here. You'll notice I've put neoprene also. And one of the things we do with this neoprene is we bring it up higher on the inside. So if water runs up against this glass and tends to pool there, that water cannot get inside the building here because gravity is keeping it from doing that. Um, this is a 3/4 inch interface here, which is what we typically say is the minimal amount and the appropriate amount when you're trying to grab hold of glass and keep it from getting moving around and maybe getting sucked out under wind suction. Um, so you need about a 3/4 inch overlap between the glass and whatever's grabbing the glass. And of course, since we want it deeper on the inside, it's more than a 3/4 inch interface. Okay, so I want you to ponder all that. I also want you to notice this 3 foot 4 inch deep dimension, which is the unobstructed. And by the way, when I say unobstructed, the unobstructed vertical dimension of the glass between the bottom of the top chord and, well, the curb down below. So this is a kind of a mullion that grabs hold of the glass. It's also the curb at the upper part. So we'll put some kind of single ply membrane that glues to that face and comes out over the top surface of this insulation. And by the way, there'll also be a 1/4 inch thick board, recovery board, because even though we call this rigid insulation, a really heavy construction worker can walk on that and do damage to it and possibly do damage to the single ply membrane on top of it. So there's a bunch of stuff that's not shown in this drawing that you would need to think about if you're going to actually bring this to fruition and get it built. Um, okay, so there are two sections down below. This section up above is cut right here. And you'll notice that in that location, it's cutting through the rigid insulation and it's cutting through the decking, which is what's shown there. Um, but it's staring at, well, actually, I guess in this location, you'd also see the curb up here, which gets deeper down at the low end. The curb has another 15 inches of depth because the sloped roof is now down here. This is the high end of this roof. This is the low end. So in this drawing, this portion of the trusses would be obscured between that line and that, but we'd still see the truss webs down below. So I need to go back and modify this drawing to show that particular issue down there. Okay, this, by the way, is north. So this is the north-facing glazing, which has no overhang to speak of. And then this is the south-facing glazing, which has a little bit of an overhang to protect it. Now, I mentioned that if we only have south-facing glass and we have, say, a sawtooth roof, then the profile angle for that overhang is greater. And then if it's just for view glass and you're trying to stop glare, that profile angle might go all the way out to 30 or 40 degrees, depending upon how urgently important it is to you to protect the space inside from glare. Okay, so I'm going to put a copy of this drawing on Google Drive so that you can go back and reference it because um, the sectional drawing through this that's included in the video is not high enough resolution for you to see it. And here you can zoom in and dimension things and figure out what you want to get out of it. Also, while I'm here, I'm going to mention the fact that you'll notice here that is a dimension of a certain style. It's a one I invented. If you just took a raw file without all this stuff, there'd be a standard and then annotate. So what I have done is I have gone through and I have created all these different sizes of dimensions. So if you want to go in here, for example, let me go take that and I'm going to say when I go over to properties, it says the dimension style is 2 inch, which means the font and the arrowheads and all that are 2 inches. But if I come back here and I hit there and I go look at this, I have a different size font and I have too many things selected here. So let me unselect one of those and I'll go here. In this dimension now, style is 1.5 inches. So because I'm looking at smaller things, I'm choosing smaller fonts and smaller arrowheads so my drawing doesn't get completely cluttered by those things. All right, so I'm going to leave this for you. I'm also going to give you a vacant file, which you already have on Moodle, and some of you have opened it because you noticed that there's nothing drawn there. Why the file is special is because of these various dimensioning tools, which are annoying to put together and don't come in the original AutoCAD file. So that's what's special about the AutoCAD file that I gave you. All right, so now we're going to go talk about your example. And in fact, we're going to talk about mine also. So we said this is going to be 60 feet across two of these bays, and the length of the base is going to be 120 feet for you. I said your insulation thickness is 6 inches. Your corrugated decking is 3 inches. And some of these things I scratched out, like that was 6.5 on this drawing. It's going to become 6 inches on yours. And I've also talked about the total drop of the slope, which starts off as 4 inches up here, and it's something more down there, depending upon how many feet. So you're going 120 feet, you're going to have a total drop of 30 inches from this end to that end of the slope portion. So that's your assignment, and there is a description here that talks about what video you go back to start with. You're also going to have this video B, which is what you're watching right now, and I will make that available to you also. I may have it as a URL or a link because I don't think I can get this up on Moodle in time. It's embedding it in Moodle is a real pain. So I'll just send it to you as a link in a message on Moodle. Okay, so all these things remain the same. They're not changing in the drawing. What changes is the spans in both directions. The vertical height of the floor to the flat ceiling above is 18 feet. Again, the depth of the corrugated decking will be 3 inches. The depth of the foam insulation will be 6 inches, and you're going to use 5 by 5 inch square tube. And this is me kind of eyeballing it from experience. May turn out that 5 by 5 is not good enough. You may need to go to 6 by 6. Um, but we're not going to actually analyze this. So, but you'll be able to look at it. And what you'll be looking at it, as I said, is the drawing that you share with your engineer, who will then go off and tell you whether 5 by 5 is good enough or not. Okay, so I already mentioned that the outside dimension of the webs are going to be, for ease of connections, they're going to be 5 inches by 5 inches also. All right, so that's your assignment. And now what I'm going to do is I'm going to go talk about the problem I'm going to work for you. And in this case, I'm going to use the 6 inch thickness of insulation, which in the tapered insulation will probably be about 8 inches at the center in order to get it tapered, but it'll be 6 inches out at the edges. And we're going to go through the calculation of the height of the glass. And I think I put that number here already, but I want you to understand where it comes from because you're going to have to find that for yourself. So in this case, since this is 100 feet long and it's a quarter of an inch per foot, we multiply a quarter of an inch per foot times 100, and we get a 25-inch drop between that end of the tapered roof and this end of the tapered roof. Okay, so we're gonna go from there. So I have a file here somewhere. This is weird. I'm sorry for the brief pause here. Um, I got some of these files out of order. So I'm going to go here and take a brief break and get a glass of water. And then